Hello everyone, this is R Saisri, pin number 22955A0517. So we are going to discuss a topic about the expansion in matrix weighted graph. So the abstraction of this topic is a matrix weighted graph is an undirected graph with a k into k positive semi-definite matrix assigned to each edge. There are natural generalizations of the Lipasian and adjacency matrices for such graphs, leading into a generalized notation of expansion. Extensions of some theorems about expansion hold for matrix-weighted graphs. In particular, an analog of this expander mixing lemma and one-half of Cheeger type inequality. These results lead to a definition of a matrix-weighted expander graph and suggest the tantalizing possibilities of families of matrix-weighted graphs with better than Ramanujan expansions. So now let us see what is a weighted graph with an example. So as an example for a weighted graph, imagine you run an airplane and you'd like a model to help you estimate fuel costs based on the routes you fly. In this example, the nodes would be airports, edges would represent flights between airports, and the weight would be the estimation of a flying cost between those airports. So the weighted graph represents the total situation of running an aeroplane. So far we've seen the weighted graph. Now let us see about the weighted and as well as unweighted graphs. As you can see, there are two diagrams. One represents the weighted graph, the other represents an unweighted graphs. So the difference we can find is the weighted graph has a certain value for each and every node or edges. The unweighted graph doesn't have any type of values for it. So when we have a values for a diagram or each node, then that is considered as a weighted graph. The graph which doesn't contain any values, it is known as an unweighted graph. So as we saw a weighted graph in the previous slide, so here we can see the weighted graph. It is a graph with numbers assigned to its edges. The weight itself, it can be either cost, distance, travel time, hop, etc. Any item may be considered as a weight for a particular given graph. So next we are going to discuss about the simple path. A simple path is a path such that all vertices are distinct except that the first and last could be the same. For example, ABCD is a simple path. Here the path simple represents a shortest way in which the execution or anything may be done in a simpler path. So next we can say a graph definition. A graph G equals to V comma E that is composed of where V represents a set of vertices that are nodes and E represents a set of edges which connects the vertices in V. An edge E equals to U or V is a pair of vertices. So an example here we can see a graph which contains A, B, C, D and E. So the V which are nodes, there are the nodes in the diagram are A, B, C, D and E, and whereas the E and edge, the edges that are pairs of vertices are A comma B is one pair, A comma C, A comma D, B comma E, C comma D, C comma E and D comma E are the E which represents a pair of vertices. So the next is representation of graph. There are two kinds of representations in which we represent our graph. One is adjacent matrix and another is adjacency list. So these two ways we can represent our graph. So the first one we're discussing is the adjacency matrix. Assume n nodes in graph. Use matrix A of 0 to n minus 1 and 0 to n minus 1. If vertex I and vertex j are adjacent in graph, that is A I of j of equals to 1, otherwise A of I and j equals to 0. If vertex I has a loop A of I and I that equals to 1, if vertex has no loop then A of I equals to 0. So here is an example of the adjacency matrix representation. So here there is a graph which consists of 0, 1, 2 and 3. The 0, 1 is connected 1 to 3 and 3 to 2, 2 to 0 and 1 to also 2. And here the simple calculation which is done in the array to obtain the required matrix. After the calculation done, here we can see the matrix which we obtained, the matrix A, which consists of zeros and 1, 4 rows and 4 columns. So here in the previous slide we saw the matrix representation, the only example which is for unweighted graphs. So here we are doing the adjacency matrix graph representation with the weighted graphs. So the previous and the same example here which is consists of 0, 1, 2 and 3, but the slight difference is in the previous the 1 is connected to 2 and here the 0 is connected to 3, and each and every vertices have their respective weights, that is 0 and 1 has a 10 weight, 1 to 3 edge has a 4 weight, 2 to 3 edge has a 5 weight and 2 to 0 the weight is 20. So in an array after the calculation done we get a matrix, the matrix A. Here we can see it consists of zeros, 4 columns and 4 rows. So now next we are going to see about the adjacency list presentation. So in an array of list, the ith element of the array is a list of the vertex that connected to the vertex I. So here is a simple diagram which consists of 0, 1, 2 and 3, and here is an array representation which consists, it says the array pointing to the next arrays. Here as we can see, the node O points to the node 2, 1 and 3. So in the first column we can see the representation, that is node 0 connected to the 1, 2 and 3 nodes, and the first node and the 1 node is only connected to the number 3 node, and the 3 node is not connected to the any node, and 2 node is connected again to the third node. Here is a simple representation of that. And vertex 0 connected to the vertex 1, 2, 3. Here is a verbal representation of the following diagram, where vertex 1 connects to the 3, vertex 2 connects to the 3. And yeah, the next is the graph, the weighted graph representation of adjacency list. The weighted graph extended each node with an additional field weight. So that is the same process in which the node 0, 1, 2, 3 consists of their respective weights. The node 0 contains the 1 to 10, that is the 10th, and the second node consists of weight 20, the third node consists of weight 1, and the first node consists of weight 0 to 10, and third 3 to 4, and the second node consists of 0 to 20 and 3 to 5, and the third node consists of 0 to 1, 1 to 4 and 2 to 5, as we can see the diagram. In this way the weighted graph representation is done. And so here is a conclusion, that the matrix weighted graphs are an expressive generalization of undirected graphs and expand the concern of spectacular graph theory to operators acting on higher dimensional spaces of function. Expansion in matrix weighted graphs has more stable behavior than in standard graphs. We have shown that spectacular measures of expansion control combinational measures of expansion, as in the expander mixing lemma and one side of Cheeger inequality. However, we don't have a conversion combinational condition for a matrix weighted graph to have a good spectacular expansion.